Uh, Good evening, one and all. Thank you so much for joining. Thank you so much for joining me for today's class. Welcome you all to the properties of materials tutorial session. This will be the third tutorial session. I really hope I'm audible. As usual, since last class, I have made some changes to my setup. I hope this feels better than the previous classes. My name is Sairam Ramchandran, and I'm a PhD student at IIT Bombay. As you all know, this is the third week of this course, Properties of Materials, Nature and Properties of Materials, Part 3, and the course code is NOC25 and MM34. The course instructor is Professor Ashish Garg from IIT Kanpur. I'll quickly go through what would we be doing in today's class, in today's tutorial session. We'll start with the tutorial for week 3. We'll solve some questions there. If we will also try to recap the previous week tutorials as well. We'll take a short break, water break for a few minutes after that, and then depending on this week's classes, uh, where we learnt about anisotropy of uh, uh, the nature of anisotropy of elastic modulus, and how can we design composites to suit our material needs for specific applications, isostress and isostrain conditions which would be applied for composites. Also, once we've learned in depth about the elastic modulus, we went into the nature of anelasticity, how it comes about, the concepts of relaxation time of that brings about the nature of that brings about the property of anelasticity, and also what are the effects of anelasticity, which include, say, damping capacity, and other such factors. So we'll take a quick look into those aspects which will form a basic revision of what happened over the course of this class. And finally, if you have any questions and or any feedback for me, please do let me know. Without much further ado, we'll get started with this week's tutorials. Um, okay, the very first question for this week is: the materials which have the same elastic properties in all directions are called. Uh, as we know, if there is any difference in materials between the x, y, and z axis, or u, v, w axis, as you want, in however way, which way we want to describe it, these axes. If there is any difference in properties along these any of these axes, then it is called anisotropy. Anisotropy, difference in properties, different properties along different axes. Okay, but when we don't see a difference in properties along different axes, then the term is called isotropy. When if we go into the uh, etymology of these terms, any term with the prefix "an" is the opposite of, and any word with the, let's say, starting terms iso, you would have heard isothermal. Professor had mentioned the term isentropic over the course of this week's classes. When you have the prefix iso, it basically means it is same, it is constant, it is not changing. So uh, when we have, well, material properties, which is especially elastic properties, same across all directions x, y, z, it is called as isotropic in nature. Mm, Second question for this week: which of the following occurs at a higher value of stress? The options are proportionality stress, true elastic limit, 0.2% of offset yield strength, stress at elastic limit. I think we should be very careful when we see the term higher value of stress over here. I think the higher value of stress is extremely relative in the sense we are still talking about stresses in the elastic region only. not we are not going into the plastic region. We are not touching the topic as of now yet. Elastic region. Okay, so within the elastic region, which of the following occurs at the highest value of stress? So in the elastic region, we are going to have a linear relation between, let's say, when we plot stress versus strain. Let's say this is sigma max for this region for this material, and then um, throughout the entire region, you are going to have the proportionality limit, and wa- true elastic limit and engineering elastic limit would ideally uh, be very similar. And what happens at the highest value of stress? So if you had seen any other stress strain graphs, let's see if you had observed the stress strain plots for steels, you would have an elastic region. uh, uh, I'm very sorry for this not being okay. Let me draw the stress strain for, let's say, steel, linear region followed by a curved region. Um, the strain corresponding to the maximum value of stress within the elastic region, this area is called as the offset, and this value of strain corresponds to 0.2% of the total yielding. So let's say if this I have definitely not drawn to scale. If this is the overall uh, limit to which this material, especially metallic materials, especially crystalline materials, can undergo can be strained. This offset region typically tends to be 0.2% of this entire will correspond to strength of 0.2% of the ultimate yield strength, and also this region will also correspond to the 0.2% of the strain. So for the answer to this question is 0.2% offset yield strength. Moving on. Third question, which of the following correctly defines an anelastic behavior? So as we would have observed in this week's class, um, what is the difference between so why did we start talking about anelastic behavior right at the beginning is that um, when we have an isothermal deformation or isothermal um, strain within the elastic region, and an adiabatic process at the same time, the tension and the compression curves are going to overlap, and then we are not going to see any changes to the strain. We are not going to see any so this will be the nature of the curve. We increase from zero load, we go to the point A, we stretch it to the elastic limit of point A, um, which will be EI, elastic limit, maximum limit, and let's say EI. And then once we release this load at the maximum load that it can withstand within the elastic limit, it comes back again to point zero. There's not going to be energy loss to the surroundings at all. However, in reality, practically, when we have depending on the strain loading rate, this is not um, how it is going to occur. So what generally happens is that in an ideal case, in an ideal case, when we have adiabatic conditions, what do we mean by adiabatic conditions? That the term adiabatic refers to uh, f- no heat exchange between my system and my surroundings. That is what adiabatic means. No heat exchange between system and surroundings. Now, under adiabatic conditions, I am inducing a tension stress in my sample. If in an ideal condition, the adiabatic tension curve should follow my isothermal curve. However, because this stress strain loading rate is probably higher, or because of so many other factors that professor had discussed in his class, or which we might look at the second half of this class during our revision, uh, the adiabatic tension curve might not follow the isothermal plot. So what happens is that it, the maximum stress is already applied within the same duration. Sigma max has already been reached. But even at sigma max, we have not reached the maximum limit of strain, but we are reaching a limit of strain which is EA. Let's say we are reaching a limit of adiabatic strain. And if we let the system equilibrate, or if we don't disturb the system at all, we have applied the sigma max to the system. Let us leave the sigma max as such to the sample. What happens is that this adiabatic strain keeps increasing to the maximum value of strain, which is supposed to be EI, right? So it does reach the value of maximum strain corresponding to the maximum stress. Even here it is sigma max EI. So it does reach EI, but it takes some time. There is some equilibration time for it to reach from say point O, A, B. It reaches point O to point A instantaneously uh, using upon applying the sigma max load. But for it to reach the maximum strain, which corresponds to point B at sigma epsilon I, it takes time. There is a certain delay in which the strain is observed. Now, what we do is we release the strain instantaneously, or we release the strain at a very fast strain rate, unloading rate. Once again, we will come to a scenario where this strain does not become go back to zero. However, what happens is that it follows a very similar slope to our OA curve. It comes down, so this is the path that we are following. It comes down to some other value, let's say C. It reaches from B to C upon instantaneous removal of the load, and it again takes some time for this system to come back from the strained condition after even after removal of load, to come back to its zero strain position, zero strain and zero stress position, to its initial position. So we have a hysteresis formed here uh, when when uh, our system, when our material shows an elastic behavior. But as we can see here, from the beginning condition to the final condition, uh, the system fully recovers because we come back to point zero, point O, where it is the same as the initial condition. So the stress and strain is fully recovered. But the only thing that has happened over here is it is time dependent. So we need time for this deformation to come back to its original state. So out of the following options, fully recoverable, yes. We know from this plot that it is not partially recoverable, which means it will come back to its original state, but it is time dependent as well. So the first option, which is fully recoverable but time dependent deformation, is the correct definition of anelastic behavior. During cyclic loading, let's go to the fourth question. During cyclic loading, hysteresis loss occurs due to anelastic deformation when uh, time for stress reversal is larger compared to relaxation time. Time for stress uh, reversal is smaller compared to relaxation time. Time for stress reversal and relax are about the same. So during cycling cooling, hysteresis loss occurs due to anelastic deformation when uh, time for the stress reversal and the relaxation time are about the same. So this is so we haven't touched upon the concept of relaxation time over here as such. So the relaxation, the time here or the equilibration time here that we mentioned between point A to point B or point between point C to point O, we can term these to be the relaxation times. Um, and when these are very similar to your stress reversals time in the case of your isothermal heating, that is what we say here. This is when we have this hysteresis loss that is occurring in our systems. So we will touch upon the concept of relaxation time when we do the rehearsals, when we do the uh, refresher of this week's classes later. Okay, moving on to the fifth question. A tensile load of 100 Newton is applied to uh, aluminum boride composite of 1 mm square cross-sectional area. The volume of the parallel fiber is 30%. What is the stress in the fibers when loading axis is parallel to the fibers? Okay, I will come back to this question because uh, in the uh, in the class notes, professor would have mentioned about see various conditions such as isostress and isostrain conditions for composites. I have planned to derive the formulae for this during our revision. We'll derive these two formulas and then we'll take up this example while we are doing the problem. Okay. With an increase in the bond energy, uh, what could happen? A coefficient of thermal expansion increases, elastic moduli increases, UTS increases, ultimate tensile strength increases, or the fracture toughness increases. Um, as we even the last lecture of the previous week, the 10th lecture and the first lecture of this week, um, we discussed about the atomic nature of elastic moduli. So this is basically, let's say if we have multiple atoms stacked together and it is spaced by some distance r, equally spaced. Um, what is going to happen when we try to push together two of these atoms close to each other or away from each other? What is going to be the potential energy difference with respect to distance? Let's say U be the potential energy and R being the distance. Um, let's say we have two atoms close to each other. I'll take two pens just for example. Let's say we have two atoms close to each other. What we have surrounding these two atoms is we have a nucleus which is positively charged. We have an electron cloud which is negatively charged around both these atoms. When we provide a force to move these two closer to each other, initially there are going to be multiple reactions happening between these two. What is it? The electron cloud, so in an atom, the electron cloud of this atom is already positively attracted towards the nucleus of this particular atom. So let's say this atom A, this is atom B. The electron cloud of atom A is attracted towards the nucleus of atom A, and individual electrons in atom A repel each other as well. When we take atom B, we are going to have the same effects. Electrons of atom A are going to repel each other. The electron cloud is going to be attracted towards towards the nucleus of atom A as well. When we bring these two closer together, electrons from cloud B might also be attracted from the by the nucleus of atom A. Similarly, electrons of atom A could be attracted towards the nucleus of atom B. This is one possibility. Also, the electrons between atom A and atom B will repel each other. Nucleus of atom A and atom B will repel each other. These are possible uh, reactions that occur during uh, that occur when we try to bring two atoms closer to each other. So bond energy is nothing but the energy between these two atoms, right? Um, and the distance between these two atoms play a pivotal role in determining how what is going to happen when we bring these two together, or when we move these two together, or how difficult is it going to be. Um, so when we try to bring these two together beyond a certain limit, there's going to be a very high repulsion force between the two nuclei, which is heavier, and the electron clouds of these two, because the electron clouds are going to constantly repel along, and after a certain distance, even the nuclei will start repelling each other as well. So uh, at a certain point, the potential energy is going to be very, very high, um, that it is going to repel each other. But after a certain point, after a certain distance, let's say R1, there is going to be a decrease in potential as well. So we are going to see a negative potential to a certain point, where we will go to the lowest possible value of potential, U min, and then this is going to increase, and the R corresponding to the minimum value of the potential energy is called R naught, and this is the ideal distance of separation. So with an increase in the bond energy, when the bond energy between two atoms are very high, it basically depicts that the elastic modulus of these two atoms are very high. Um, we have seen this in various examples, such as the E of diamond and E of graphite. E of diamond is around 1100 GPa, let's say, approximately, and E of graphite is approximately 8 GPa, if I'm not mistaken. From we can check these from sir's notes. Um, it is still the carbon-carbon bond. But what is going to be the difference in these things? The structure of diamond, which is a tetrahedral structure, and where we are going graphite, where we are going to have long sheets of graphite, sheets of graphite which are bonded by very weak forces. The Along the plane of graphite, it's going to have very high modulus because it's the same carbon-carbon bond. But between two graphite sheets, it's going to have very weak forces between these two. So this is very weak forces, probably something like van der Waals forces. So this is the reason why graphite has very low bond energy. It's a very low bond energy, very low value of young elastic modulus, whereas a diamond has very high value of elastic modulus. Um, why did I explain the entire potential energy versus distance thing to explain elastic modulus? Uh, for atoms or elements with higher bond energy, this U versus R is going to be deeper and more negative. For the deeper and more negative for higher bond energy. For atoms with lo- low bond energy, we will have uh, a low, a shallow, and a shallower pit, which is not not so no, not excessively negative. It will have something like this. Let's say it could be something of this sort depicted by. Okay. The answer for this question, which is any with an increase in the bond energy, the elastic modulus increases. Okay, moving to the next question. The modulus of elasticity is, we know this very well. We have been looking at this from the very first class, which is, let's say, if we write the Hooke's law in its generalized form, sigma ij equals E I j k l into epsilon k l. So here the Young's modulus is written as E I j k l, which is a fourth rank tensor. And we also know that EIJKL, because it's direction dependent, it is anisotropic in nature. Anisotropic in nature. So the answer for this question, the modulus of elasticity, is anisotropic and a fourth rank tensor as well. Okay. Moving to the next question, the eighth question is, which of the following is the continuous phase of a composite material? Um, let's say if this is a composite, a depiction of a composite, uh, we know that the small faces that are suspended in the continuous phase, this is called the reinforcement, and the continuous phase is called the matrix. Okay, so the continuous phase of a composite material is called the matrix. Moving on, an anelastic behavior of materials involves which of the following phenomenon? um, we know that anelastic behavior occurs due to diffusion. So I would have explained that it can happen because of interstitial atoms, substitution atoms, uh, thermal currents between intercrystalline or transcrystalline, also because of dislocation movements, because of grain boundary movements, grain boundary effects. So which means all of these phenomenon occur mainly due to diffusion of atoms from one region to another. This would have been explained in Sir's third video, where he explained what happens when stress is applied to a steel, where the carbon atom is dislocated from one position and moves to another position. So diffusion is a very important uh, phenomenon which occurs which occurs in an elastic behavior. Also, because of the concept of diffusion and the hysteresis, the energy loss that happens as a part of an elasticity, there is the concept of damping as well. The other options being fatigue and time dependent plastic deformation. Time dependent plastic, these are not a part of anelastic behavior. For crystalline material, adiabatic expansion will, as we had been discussing earlier, we had discussed about this earlier. During adiabatic expansion, there is going to be a cooling during tension, and during adiabatic in an adiabatic process, upon compression, it is going to heat up the process. It is going to heat up the system. Okay. During adiabatic expansion, I'll write that down again. During adiabatic expansion, for to cooling and adiabatic compression leads to heating. Okay, we can derive this from simple Gibbs phase rules, where let's say PV equals nRT. We know this ideal gas law, and in adiabatic expansion we also know that there is no heat exchange happening. So when in an adiabatic system, when a system moves from P1 V1 T1 to P2 V2 T2, what is going to be the change when volume is changing here but the pressure will not change? There's no heat exchange. So what will happen to the temperature, we can understand from uh, these equations here. So the answer for this adiabatic expansion will cool the sample. 11th question is, the ability of a material to dash is indicated by its damping capacity. Um, as we know, a damping capacity indicates the ability of a material to absorb vibration and absorb shock. If a rubber is heated under tensile force, it will shrink. Why? For rubber, alpha is less than 0, the coefficient of thermal expansion is less than 0. So which means when we heat, it tends to shrink generally. And under tensile force, this is going to be even more prominent. Yeah. The 13th question, in the potential energy versus atomic separation, potential U versus atomic separation R plot, for R less than R naught equilibrium separation, materials with higher bond energy will result in a large. So in the potential energy versus atomic separation plot for R less than R naught, materials with very high bond energy will result in these materials will have a very high negative and very large and negative uh, dou U by dou R. I'll just draw the potential energy versus atomic separation diagrams for two different materials, one with higher bond energy and one with lower bond energy, and then we'll be able to compare. So let's say this is the material with very high bond energy. And let us also assume, just for simplicity's sake, let us also assume that the R naught is being constant. So let this be the R naught for the system. Then blue corresponds to low bond energy, orange system corresponds to high bond energy. As you can see here, this is the point R naught. At R less than R naught, when we move this side, if I draw a line at any R less than R naught, as we can see from here, these are the corresponding values of U L and UH, corresponding low and high. We can see that modulus of U high H is greater than UL, right? So which means if I don't consider the negative value of the system, then UH is going to be far greater than UL because of the nature of the curve. And as we all know, both these values are negative. So the correct option is going to be large and negative du by dr. The slope of these things are extremely negative, large and negative. Okay. 14th question. the elastic modulus of a material cannot be increased by um, when we make composites by adding second phase. We deliberately try and increase, we do that as a method to try and increase the elastic modulus of our material, so that is not the answer. Structural texturing is also when we have polycrystalline material and when we try and align it, we are trying to make the elastic modulus better, or make changes to the elastic modulus. um, Even with alloying, we are going to be changing the composition, so which means the bond energies will change. How will in the case of alloying, let's say we have an AB alloy. Okay, we have an AB alloy. We are going to have three different combinations of bonding, which is AA bond, BB bond, and the AB bond that we have. So we are going to have three different bond energies, and a combination of these things with the atomic fraction or the volume fraction of these three different kinds of bonds is going it basically becomes a composite of two or three elements, in the crudest of terms. And it is definitely going to make some changes to the elastic moduli. Um, but if we have the same sample, we are not changing its composition, we are not adding any secondary phases to make it a composite, or inducing some structural texturing, or we are just doing some simple heat treatment. Let's say we are doing some annealing or we are doing some quenching. These things are not directly going to impact my elastic modulus, because these are not changing the bond energy of my let's say mm bond, initial bond. There's not going to be any change to my initial bond energy. So upon heat treatment, it is not necessarily going to increase my elastic modulus, or it is not going to necessarily change anything with my elastic moduli. The final question for from this week is: during an anelastic deformation, relaxation time increases. So as we know, uh, the anelastic deformation is an Arrhenius is temperature dependent because it has diffusion components. Because of diffusion components and the Arrhenius nature, it is definitely dependent, let's say, on temperature. So tau equals tau naught e power q by kBT. So this is the Arrhenius nature of relaxation time. Okay, as we can see from here, um, tau increases if q increases. Let's say if the activation energy q here, q is activation energy, T is the temperature. We would like to increase the exponent of E given here. When we are able to achieve that, we would be able to increase the relaxation time. So how do we go about it? We either increase Q or decrease T. So tau will increase if we increase Q, tau will also increase if we decrease T. If temperature decreases, tau will increase. These are two possibilities by which we can, and this is the nature of any Arrhenius plot in general. So if you take diffusion, if you take um, say the energy required to cross a potential barrier, or any of these Arrhenius plots, we will find very similar relations. So yes, so the temp as temperature decreases, activation energy increases. We have two options for this, sir. Okay. Um, we'll do a recap of previous week's tutorials as well. We'll do a quick recap of those things. Uh, True strain tends to be equal to engineering strain at very small values of strain. Why do we say this? We say this because, let's say, uh, engineering strain engineering strain E equals del L by L naught, and true strain epsilon equals uh, ln of 1 plus E. And how did this even come about? It is basically ln of, so epsilon equals ln of LF by L naught. If we add and subtract L naught to the numerator over here, it becomes epsilon equals ln of LF minus L naught plus L naught. Sorry, epsilon equals ln of LF minus L naught plus L naught by L naught. We know that LF minus L naught by L naught, if we have this term separately, this is nothing but E that we have over here, where del L is LF minus L naught by L naught. Okay, so epsilon becomes ln of E plus L naught by L naught becomes 1, E plus 1. So this is um, the correlation between true strain and engineering strain. And we have seen from previous examples that when the engineering strain is very low, when it is say 0, 10 power minus 3, 10 power minus 4, then ln of 1.001 will be uh, the similar value as what engineering strain is. So there will not be any difference. But when the engineering strain increases to say zero point 0.1 or 1, ln 1.1 and ln 2 are very different from the value of E equals zero point 0.1 and E equals 1. So ln 1.1 and ln 1.2, let me just I don't remember those values, so let me just calculate them if necessary. I know ln 2 is 0.93, if I'm not mistaken, 0.693. Ln 2 is, yeah, 0.693. So epsilon becomes, for E equals 1, epsilon becomes 0.693. For being zero point 0.1, epsilon becomes 0.095. So these are not very similar, these are quite different. So that's why only at very small strain values, the true strain tends to be equal to the engineering strain. Strain is a second rank tensor, we know this. If we reiterate the Hooke's law, sigma ij equals Eij KL epsilon KL or EKL. So stress strain is a second rank tensor. So is the stress. This is the elastic modulus is a fourth rank tensor. The modulus of elasticity, as we described just over here, it is a fourth rank tensor. The stress strain curve is linear up to the stress strain curve is linear up to the proportionality limit, beyond which, when we go to ultimate tensile strength or the fracture point, we go into the plastic region. It is linear only in the elastic region, and elastic region is where your stress is directly proportional to strain. So, till the proportionality limit. What is the average linear strain produced when a solid bar is extended from 1 meter to 1.5 meter? Average linear strain, which is engineering strain, E equals LF minus L naught by L naught is the formula. Here L naught is 1 meter, LF is 1.5 meter. If we do this, 1.5 minus 1 by 1 gives us 0.5. The value of this is 0.5. For an isotropic, homogeneous and elastic material obeying Hooke's law, the number of independent elastic constants is 3. Among the following materials, Which one doesn't follow Hooke's law? We know that rubber does not follow Hooke's law. Steel, copper, and aluminum, all three follow Hooke's law properly. Crystalline in nature. Um, Rubber has very different properties. Which of the following is a composite material? Again, this is a polymer. This is steel. It's a metal. Wood is the only thing which is a composite material over here. Which of the following properties is dimensionless? Once again, we know bulk modulus is related to Poisson's ratio, everything. So it has a GPA. Kinematic viscosity also has its unit surface tension as well. Only strain, because it is del L by L. So let's say the units become meter by meter. If it's cancelled out, this is only dimensionless quantity. Um, if the radius of a wire is stretched by a load is doubled, if the radius of wire stretched by a load is doubled, then what would happen to its Young's modulus? We know for a matter of fact that Young's modulus of a material is its intrinsic property. It does not depend on the kind of load that it is applied on the material, the kind of heat treatment is done on the material, unless and until the composition remains the same. If there is no addition of any secondary phases, if there is no addition of any texturing or any alloying elements, the Young's modulus E is going to remain same. Only when there is anything that might change the bond energy of the system will there be any change to our Young's modulus. Till the time the bond energy of the system, which is dependent on the composition, which is dependent on um, uh, the elements present, the nature of the system that is preserved, it is going to remain unaffected. So the answer for this is also the same. It will remain unaffected. Tutorials. Shear stress sigma ij is defined as ij equals fi by aj. Fi by aj. Last option. Okay. Um, if sigma x equals 10 MPa, sigma y is 15 MPa, and sigma z is minus 8 MPa, then the first is stress invariant I1 is given as sigma x plus sigma y plus sigma z. So there is one small error. So it will be 10 plus 15 minus 8. So this gives rise to plus 17 MPa. Where we have 7 here, it should be 17, and this is the right answer. Which of the following is true for a general stress tensor? So we know for a general stress tensor, to simplify and to take into consideration what is it called? Uh, okay, the mirror images or so sigma ij becomes equal sigma ij equals sigma ji if or for oh, sorry if when I not equal j. So we know sigma 1 2 equals sigma 2 1, and sigma 1 3 equals sigma 3 1, sigma 2 3 equals sigma 3 2. We know the same is the case with epsilon 1 2 equals epsilon 2 1, epsilon 1 3 equals epsilon 3 1, epsilon 2 3 equals epsilon 3 2 as well. We know this is true. Okay. The final one, consider transformation of stresses from one orthogonal system to another. Assume that shear stresses were zero in the original system. The stress tensor for a new axis system will be, we know that sigma 1 prime equals summation L uh, Mn, where here I and j are 1 dash. So 3 n equals 1 to 3. Uh, Here it has been very well mentioned that all the shear stress components are zero. So which means sigma ij equals sigma ji equals 0 for I not equal to j, right? So where in any case, or rather, um, this we can rewrite as sigma mn equals sigma nm equals 0 for m not equal to n. Okay, so only if m and n values are same, then this equation run true. So which means sigma 1 prime basically becomes L1 prime 1 L1 prime 1 sigma 1 1 plus L1 prime 2 L1 prime 2 sigma 2 2 plus L1 prime 3 L1 prime 3 sigma 3 3. Because if we have any other value of m and n, let's say L1 prime 2 L1 prime 1 sigma 2 1, we know that sigma 2 1 is 0, because it's mentioned that all shear stress components were 0 in the original system. Or rather, if we have L1 prime 1, L1 prime 2, sigma 1 2, this will also be 0. So anything other than M and M and N being same, every other factor will become 0, because the stress component, the sigma 1 2, sigma 2 1, sigma 1 3, sigma 3 1, sigma 2 3, sigma 3 2, all these components are 0. So only this is the correct expression for our case where the shear stresses are 0. Okay, uh, we'll do a few more problems from some other tutorial sessions as well, and then we'll take a short break, and then we'll try to go through some of we'll try to have a revision of what happened in this week's class. um, if any of you have any doubts, if you want to ask me anything, you can either uh, write it down in the comments box, or we can even please feel free to unmute and ask your doubts. This the class that happened over the last week, where professor discussed about the anelasticity, damping characteristics, relaxation time. These are very, very interesting. Um, even before we go even before we go into any of those properties, when professor talked about how can we go about designing composites, the isostrain and isostress conditions. I will derive that formula of isostrain and isostress conditions. What is going to be the modulus of elasticity in such conditions? I will derive those equations. Um, I'll get started with this. The transformation of axis for strains is applicable for small strain values. If the composition of a material remains the same, then the change in processing conditions may lead to change in. It is going to so the composition is the same as we had discussed earlier. If there is no change to the nature of bonding or the bond energy of the system, it will not change the ductility. It will not change the elastic modulus at all. Depending on the change in processing conditions, the tensile strength can change, the ductility can change, and the toughness can change, but the elastic modulus will remain exactly the same. The elastic modulus of most metals lies in the range of um 50 to 600 GPa. For metals, if we go down the column in the periodic table, then the elastic modulus. So um, as we go down the elastic model, as we go down the periodic table, let's say uh, carbon, silicon, germanium. When we go down, E decreases because the size of the atom, let's say size of the atom R increases, and as we know, as we the R increases with time, uh, it is going to be there's something called as electron shielding. The nucleus of these two atoms are going to have a very tough time having an influence on a secondary atom because of the shielding effect of the electrons in this existing system, in this existing atom. Because of this effect, as we go down, the elastic modulus decreases. What will be the approximate value of elastic modulus of a material if the shear modulus is 150 giganewton per meter square? G is 150 Newton per meter square. We know the Poisson's ratio is zero point 0.3. E, we should find out E. We know the relation between E and G. Uh, we know that E equals G into 1 G into 2 into 1 plus nu. Okay, we know G here. E becomes 150 to 2 into 1 plus zero point 0.3, which is 1.3, doubling is 2.6, 0.6. Um, so 15 into 26 becomes 390. The units will remain the same as G because Poisson's ratio is unitless. So the answer is 390 Newton per meter square. For incompressible fluids, the value of bulk elastic moduli is infinity. Why is that the case? G equals. So when we talk about G, um, how have we derived G? Um, the value of, so for incompressible fluids, the value of bulk modulus, bulk elastic moduli is infinity. Just give me a minute. I'm very sorry. Yeah. What is bulk modulus? Your K. What is your bulk modulus? K. And what is the formula for K? K is sigma hydrostatic by change in volume, right? When we say that the fluid is incompressible, then it means that delta V is zero and your negative term tends to zero. So this basically becomes sigma hydrostatic by zero. So which tends to infinity, right? Right. So K tends to infinity. Three fluids 1, 2, and 3 have bulk modulus K1, K2, K3. And we know if K1 is greater than K2 is greater than K3, then which fluid will have the highest value of compressibility? Again, following the same principle where we know K is sigma hydrostatic by del V by V naught. So if we take this basically becomes sigma hyd into V naught, let by del V, assuming sigma hydrostatic and the initial volume are exactly the same for all three liquid fluids, then this becomes a constant. We are basically dealing with inverse proportionality between um, uh, compressibility and the bulk elastic modulus. So if the bulk elastic modulus, if K is high, del V is low. So K3 has the lowest, so del V should be highest. So if K1 is greater than K2 is greater than K3, then del V3 greater than del V2 greater than del V1, where if the bulk modulus of 1 is greater than 2 is greater than 3, then the compressibility of fluid 3 will be greater than the fluidity compressibility of fluid 2 will be greater than the compressibility of fluid 1. That is what I meant. The strong bonding in materials lead to high modulus of elasticity and low coefficient of thermal expansion. These are answers. In an experiment, the bulk modulus of elasticity of a material is thrice its shear modulus. K equals 3 times G. Okay. The Poisson's ratio of the material is, see, we know that K equals E by 3 into 1 minus 2 nu, and we know G equals E by 2 into 1 plus nu. We know that K equals 3G. and we'll substitute g over here. 3 into e by 2 into 1 plus nu equals e by 3 minus 6 nu. Okay, we'll take it this side. 9e minus 18 nu equals 2e plus 2e nu. Okay, bring it this side, bring it this side. So it becomes 7e equals 20e nu. So nu basically is 7 by 20. We have 7 by 20 over here. What will be the value of the Poisson's ratio if the Young's modulus is equal to the bulk modulus? We saw that k equals e into 3 into 1 minus 2 nu. If k equals e, then this becomes 1. So 3 minus 6 nu equals 1. 6 nu equals 2. Nu equals 1 by 3. Okay. What are the limiting values of Poisson's ratio? It's 0 to zero point 0.5. A bar of diameter 40 mm and length 40 centimeter is subject to an axial load of 100 kilonewton. If the bar is elongates by 0.005 mm, the Poisson's ratio of the material of the bar is 0.33. I did this problem in detail in previous class. Which of the following is or are true if the value of Poisson's ratio for a material is 0? Um, if nu is 0, then we can very clearly say that the material is rigid. Longitudinal strain in the material is infinite. There is no longitudinal strain in the material. The material is rigid is the correct answer. If the value of modulus of elasticity and Poisson's ratio are 300 and 0.5, what is going to be the value of the shear modulus? G equals E by 2 into 1 plus nu. So G equals 300 by 2 into 1.5, which is 300 by 3. This is the correct answer. Okay, final question. The potential energy of atoms at the equilibrium position is, so when we talk about equilibrium position, which means R equals R naught, the potential energy of atoms at the equilibrium position is at its minimum. This corresponds to the EU minimum value. Okay, we are done with the tutorials for this session. Um, the 12th question, right? Yeah. Uh, yeah. Uh, can I come back to this at the end of the class? Because even if you're not, if I'm, even if I'm unable to come back to this question, uh, the detailed explanation is in the previous video, so which is already uploaded on YouTube. You can definitely refer to that as well. Okay, I'll just take a few minutes break. Uh, we'll take a short break. Yeah, after this, we'll have a recap of what Professor has taught this week, and then we should be good to go. If you have any doubts, please do let me know. We can take it as such. Um, Thank you. Let's get started again with a quick revision of this week's class. We have around half an hour. Um, this week's the lectures for this week, we started from we again started from where we left off last time, where we discussed the atomistic approach, where we discussed the atomistic approach uh, to elasticity. We basically saw if we have two atoms, what is going to be the nature of potential energy when we try to bring two atoms close to each other or try to separate those two atoms away from each other. Um, what is going to be the nature of it? What would be the nature of these potential wells between, let's say, elements or atoms with higher bond energies or some with lower bond energies, and what would be the corresponding moduli for these two. Let's say the blue over here is low bond energy material, orange corresponds to high bond energy material. Which one do we think would have the higher moduli? So um, we know from the class that the elastic moduli for high bond energy material is going to be higher than the elastic moduli for low bond energy material. We saw the formula behind it where the potential energy U can be written as where we have an for this corresponds to the force of attraction, this corresponds to repulsion. We know very well why is there an attraction and repulsion between these two atoms. So we can have these following changes, which is uh, let's say we have atom A and atom B. There is definitely going to be there's definitely going to be attraction between electron of atom A and nucleus of atom B. Similarly, with electron of atom B and nucleus of atom A, there is going to be repulsion. So we'll complete the other thing as well. So electron of atom A and nucleus of atom A, and electron of atom B and nucleus of atom B. We are going to have these four following attractive forces. We will have a repulsive nature of the following reactions, which is the electron of atom A and electron of atom B are going to repel each other. The neutron of atom A and the nucleus, sorry, the nucleus of atom A and the nucleus of atom B are going to repel each other. So these are the following reactions that we will generally see. So it is basically a combination of all these things together, how we are able to plot this potential energy versus our graph. Similarly with the force as well. So uh, when we try to bring two atoms together beyond the certain limit r naught, we are going to need a very high positive force, because at distances less than r naught, we had initially at the beginning of this class we had assumed these two to be two atoms. When we try to bring these two pens together beyond their ideal limit r naught, where their potential energy is minimum, we are going to need a very excessive positive force, because there's going to be so much repulsive forces against these two atoms, because of the repulsion between these two nuclei, repulsion between these two electronic clouds. There's going to be excessive repulsive force between these two, so it tends to move away to the ideal distance r naught. But because of the repulsive nature is so high, it'll move away from r naught, and then it'll start experiencing an attractive force. It'll come again, move again, come again, move again, come again. So this is what generally happens, and that's why we say that atoms are constantly oscillating about its mean position. Uh, whenever there is some temperature or there is some energy involved. Okay. Uh, so when we plot the potential energy versus R and the F versus R graph, so if we continue this for F versus R, so this is the point. So it will be slightly different, where rather than following rather than the force becoming zero here, the force will become zero here, the force will be zero here, and then it will continue to be negative and then move away. Okay, so this becomes r naught. Sorry for may not being in a straight line, but this is what I had intended to draw. Okay. Uh, from this, we got to know from previous videos, we got to know that the modulus of elasticity is a fundamental property of the material, and it is primarily determined by the bonding characteristics, the nature of bonding um, between two atoms in a given material. So as the bond energy increases, we know that Young's modulus increases, and also Young's modulus increases if we have strong bonds, then it presents a deep and narrow well, leading to higher curvature. So the curvature here, if we plot tangents over here, these places, we'll have very high curvatures. All these things correspond to higher value of Young's moduli. But when we have very weak bonds, uh, what could be weak bonds? Say, hydrogen bonding or van der Waals forces. These are the potential energy versus distance of these are very broad and very shallow. They have, when we try to draw the tangents, they have very low curvatures. So this df by dr is nothing but the tangent at any given point of to this curve, as we all know from basic mathematics. So when we try to measure the tangent for any of these for any of these points, it will be the curvature will be very low, the value of the tangent will be very low, the slope of the tangent will be very low. Uh, yeah, so all these corresponds to small e as well. So one very common example, very simple example that is discussed time and again in this is graphite. Yes, yes. So just see here. So E for graphite as I'll use a different color. E for graphite is 8 GPa, whereas E for diamond is around 1150 GPa. Why is that the case? Graphite, as you know, is defined as a single sheet of carbon atoms which are uh, arranged in this particular way. And however, the bonding between two different layers of graphite sheets are not very strong. They are not covalently bonded. They have very weak van der Waals forces of attraction between those two parallel sheets. So when if we try to measure the moduli of the graphite sheet along parallel to their sheets, then it is also very high. The E11A is very similar to 950 GPA, which is pretty similar to the 1100 GPA that diamond has. Um, or no, not pretty similar, but it is considerably high. It's very high. What we expect from a carbon-carbon bond. But because of the very weak van der Waals forces, we always say the uh, weakest link, right? Uh, always target the weakest link. So the weakest link here is the bonding in between the two parallel sheets of graphite, which has very small values of elastic moduli. So as a combination of these two together, we have a very low value of elastic moduli for graphite, whereas for diamond, which follows the tetrahedral structure, has a very high value of elastic moduli. So we have also seen that when we go across the periodic table, um, we can see an increase in across periodic table. You can see an increase in E. We can also see as we come down the periodic table, E decreases. We have seen all these things from various examples. We have also seen this with an example of along with data from their melting points as well. So I'm sorry. I, Okay. Um, So, so professor had given these examples of various metals such as tin, zinc, silver, aluminum, copper, alpha iron, and then tungsten as well, because he wanted to discuss about the bond energies of the relation with bond energies. Elements or materials with very high bond energies typically tend to have very high melting points as well. So let's say tungsten has a very high melting point, alpha iron has a very high melting point, same with copper and silver as well. All these have melting points higher than 1000 degrees, and we can see subsequently they have much higher corresponding values of sorry, they have much higher corresponding values of Young's moduli as well. And so with increasing bond energy, we'll definitely be able to see an increasing with increasing bond energy. We'll see an increasing trend of Young's moduli as well. In the case of ionic solids, as we've seen here, NaCl not so much, but proper ceramics like magnesium MgO, alumina, and titanium carbide. See, even I have solids like tungsten carbide, um, YSZ, which is yttria, stabilized zirconia. All these things have a very high value of Young's modulus because of their structure and because of the bond strength between the atoms here. Um, Similarly, in the case of polymers, we see that polyethylene, PE, polystyrene, PS, have uh, polyethylene, which we use as normal polyethylene plastic bags that we use in our daily lives. They have very, very, very low values of elastic moduli. In the case of polystyrene, it is considerably better than, let's say, a polyethylene, but it is still very low as compared to any of the above mentioned values that we have discussed here. So let's say as mentioned here in the case of metals, it is in the range of 100 to 600. In the case of there are something less than that. Let's say 10 is less than that. Aluminum is closer to 60, 70 GPA than 100, but still we can expand the limit to 50 to 600 GPA, not more than that. But as we see here, the values of alumina are pretty high. They are closer to the range of the 600 GPA than to the lower end. Um, so all these things are finally dependent on the bond strength or the bond energy and the elastic modulus. We see a very direct correlation between these two. Uh, Again, we see uh, correlation between the elastic modulus and the melting points and the bond strength as well. So if we have a tripartite uh, vision of all these three, we can observe what is the relation, what is the nature of we can so um, if we are given the information about the bond strength and the uh, melting point or the melting point and the elastic modulus, we should be able to take a guess about the nature of bond strength between, let's say, four or five different atoms, four or five different elements as well. So, uh, that is the sort of correlation that has formed between these different types of atoms. So, why are we looking into these aspects? Is because in real life application, um, seldom are we going to come across an application where we want only hardness. We want it to be extremely hard, or we want it to have an extremely high value of elastic modulus, and we don't want any other properties. Seldom are we going to have properties with only one need. We are going to have a combination of requirements which cannot be satisfied by a single material. So that's why we have gone for something called as a composite material. Composite, as the basic English definition can suggest, it is a composition of multiple elements together, multiple things together. So a combination of multiple things together. That is what comes to a composite. So we can design, strategize, and design composite materials to make new materials, uh, which have which have properties which are suitable and which are very good in specific properties that we need for the desired application. Say, for example, in the very first class, we were discussing, um, let's take the case of, let's say, I'll just create a new note. Let's say we'll just take the case of um, the Titanic, okay, which is a ship. What do we need to build ships? Um, we need it to be very, very tough. See, understand the term that I'm using right now. I did not say that it needs to be very hard. I said that it needs to be very tough. Okay. So, uh, why do I need it to be very tough? Even in the worst case scenario, if it comes in contact with with another ship, with a rock or something else, I don't want my ship, the hull of the ship, to tear apart. I don't want my hull of the ship to break apart. So these are important requirements for a material that I'm going to be used for building a ship. But in the case of Titanic, because of some property of the material that was used, which I had termed that DBTT, ductile to brittle transition, which happened in that case, uh, because of this transition from ductile, so steel, as we know, we can bend steel, we can make it into plates, different shapes, which shows the ductility of steel. But in that particular case, because the steel was traveling in sub-zero water temperatures in the Atlantic, uh, it underwent something called as ductile to brittle transition, where the ductile steel became extremely brittle. So that's why when the moment it came into contact with the iceberg, it broke. Um, it shredded into pieces. There was a huge tear in the hull. A lot of these things happen. So we, so when we have such applications and when we are going to do, when we need a new material for ships, we should make sure that it is not that it does not undergo DBDT. It does should not occur. Can one single piece of steel or iron, will it be able to do this? No. So we need more specialized steels. Um, Along with the very good toughness, it should also be corrosion resistant, right? Because it is traveling in salt water. We know, we have seen our house gates, our cycles, and a lot of other things, our silencers, a lot of these things getting rusted when it is exposed to rain and is exposed to atmosphere and a lot of other things. So, especially when it is traveling in salt water for throughout its journey, we need to make sure that it is corrosion resistant as well. In some cases, it is not possible to accommodate these things through a material requirement only. So um, we include as um, a secondary phase, let's say something like paint or some alloying mixture or something of that sort. Uh, all these things together is what is called as a composite. Okay, when we can think of any n number of real-time, real-world examples, and we will come up with composites. One more very simple example. I am from Mumbai, um, and in Mumbai, it rains for 3 months continuously. We have umbrellas, right? What happens in umbrellas? So it is just a piece of cloth, but uh, f- can we think of it as a composite as well? Yes, it is a composite, because if it is just a simple piece of cloth, it will not have the tension. When it rains, when there is a heavy downpour, it is going to soak and it is going to not withstand its shape. Only because of the long rods that are kept in between are we able to see the structure of an umbrella is also technically a composite, right? So the long rods in between keeps the cloth tight, and the cloth nature of the cloth material is such that it does not become completely wet upon exposure to water, upon exposure to rain. So These are simple real-time, real-world examples of how and where composites are being used for us. Okay, um, there can be multiple classes of composites depending on how they are made, how they are used. So, what is basically a composite is that we need a major phase in which there is going to be some reinforcement, there is going to be some addition, which are going to help us improve the property of this main phase, right? So, and there are two ways in which this addition can be added. It can be added randomly as particles, as dots, or it can have certain shapes. Some plates, flakes can also occur, or it can also happen as it is shown here in the form. Please give me a minute. Sorry for the delay. Um, it can also happen in the form of these fibers, um, and these are called these are fiber reinforced composites. That's a general term for such composites. Okay, and also depending on the axis in which how these are stretched, we can make sure we can align these fibers, we can align these particles in such a way that it is going to give us the best results. Okay, so this is where I mentioned that we will go through this derivation once. Okay, um, so when we are talking about the modulus of elasticity, modulus of elasticity of composites, we have two major conditions. Let's assume in this case, let's assume a fiber reinforce or anything for that matter, does not matter. Okay, we can either load them in this fashion, sigma, or we can apply load in this fashion. Let's say sigma 2. Okay, depending on how we load it, sigma 1 falls under what we call as isostrain condition, and sigma 2 falls under what we call as isostress condition. As I mentioned initially, the word ISO refers to something being same across. So in the case of, let's say, let's take the case of ISO strain condition. What is the actual condition for ISO strain? As we see here, ISO strain. So we have before that we have what do we have? We need to find the elastic modulus of the composite, and we have two things. We have elastic modulus of the material of the matrix EM, and the reinforcement EF or something, particle, let's say EF, particle fiber reinforcement. Mind you, these dots can still be fibers, but the fibers would be in and out of the plane. So these dots would still be fibers in and out of the plane, which is viewed from a different side, as simple as that. So, okay, fibers. So we need to find EC, that is our task. For isostrain condition, we know that the strain of the composite is the same strain for the matrix, same strain is applied for the fibers as well, for the reinforcements as well. And we know from basic condition, so the overall stress should match. Sigma for the composite should be the stress on the matrix plus the stress on the reinforcement. So we know from Hooke's law that sigma equals E into epsilon. So let's replace the terms here. Sigma C, okay, EC into EC equals EM into EM plus EF into epsilon F. So we know that from the very first understanding is that EC equals EM is equal to EF. So we can straight away cancel these. So we end up for isostrain condition, we end up with the logic where EC equals EM plus EF. Okay, so your isostrain condition is very similar to your resistors in series, right? Is similar to resistors in series. Now let's come to isostrain condition, isostress condition. So isostress condition basically means sigma C equals sigma M equals sigma F. And in this case, our epsilon M equals epsilon C, sorry, plus epsilon F. This should be satisfied. So now epsilon equals sigma by E, right? So let us substitute. So sigma C by EC equals sigma M by EM plus sigma F by EF. So we know that sigma C equals sigma M equals sigma F. So we end up with 1 by EC equals 1 by EM plus 1 by EF. Okay, this is where professor did an example. We'll also take one more random example. So let's say example, we have a material where my matrix Young's modulus is around 300 GPa and my fiber matrix is fiber, this is around 2 GPa. My volume fraction of my fiber, the main thing that I left out in all these things is that we should always consider the volume fraction of, let's say, the volume fraction of my matrix and my volume fraction of my reinforcement. So EC will technically become FMEM into FFEF, where F is the volume fraction of that particular component. So from From here we can see this is the case, and the same volume fraction is going to apply for our isostress condition as well. So it will be here fm, so it will be here. Okay, we'll continue the example. Let's say the volume fraction of the fiber or the reinforcement is around 30%. So what is going to let us try and compute the values of the elastic modulus of the composite in both isostress and isostrain condition. So we know if Vf is the volume should be conserved. So if Vf is 30%, then we know for a matter of fact that Vm is 70%. Okay. So in under isostrain first, Vf Ef plus Vm Em. So Vf is zero point 0.3 into Ef is 2 plus Vm is zero point 0.7 into 300. 210.6 GPa is the overall value of the overall Young's modulus of the composite in isostrain condition. Under isostress condition, one can always ask uh, uh, the overall modulus of the composite seems to be lower than the overall modulus of the matrix phase in general. But what if the matrix phase had a very high value of EM, but it did not have a very good value of, say, let's say, fracture toughness, or if it were extremely brittle in the case of ceramics. So, but let's say the fiber that we have reinforced, it is like a plastic. It is not brittle. It has very good load bearing capacity along certain directions. Under such cases, um, this composite, even though the entire composite in isostrain condition will have is having Young's modulus lower than that of the matrix, it could have other property. It could have better properties in some other very specific scenarios. Okay, we'll come back. In our isostress, we know EC equals FF by EF plus FM by EM. So EC becomes EF into EM divided by FF EM plus FM EF. So what is EF? We know it is 2. What is EM? We know it is 300. What is FF? We know it is zero point 0.3 plus zero point 0.7. I'll just do this calculation. But one thing that we can definitely appreciate from this calculation is that In both the cases, the Young's modulus, be it isostrain or isostress, the Young's modulus is higher than that of our reinforcement or the fiber, which was just 2 GPa. Okay, this is definitely a plus point if we are looking to strengthen or use the fiber in some way or the reinforcement in some way. Okay, um, moving back to our presentation. So we saw that this shows that we can achieve higher modulus as well, right? So I think Professor had given an example as well. Yes, E1 and E2. Uh, Even in this case, let's say the the Young's modulus is lower than that of the matrix, which is 300 GPa. Oh no, it is actually the other way around, as you can see here. As you can see here, this is a polymer ceramic composite where the ceramic is the reinforcement. Okay, and we are able to significantly improve the properties of the polymer by a slight addition of the ceramic. Probably in our case, I should have reversed the numbers. I took a random example, my mistake. Okay. Um, uh, Following this, we also discuss about what are the other factors through which we can impact the uh, Young's modulus or the elastic modulus of an element. Um, Allowing is something very important, as we had discussed earlier. Alloying is basically addition of one more layer of atoms. Uh, when we have another set of atoms in our mixture, so rather than just having AA type of bonds, we'll also have BB type of bonds, and we'll also have a composite AB type of bond. So as it is given here, copper zinc system, pure copper will have only copper copper type of bond, pure zinc will have zinc zinc type of bond. But in a copper zinc system, it will have copper copper, copper zinc, and zinc zinc type of bonds. All these three things together. So because there is a change in the nature, change in the bonding energies, overall bonding energies, there is going to be a change in the Young's modulus as well for a copper zinc system. And uh, when we try and incorporate some sort of anisotropy in the structure or anisotropy to, or rather than saying anisotropy, if we add some texture to our material, that is going to give us that is going to give an improvement in my Young's modulus, as we can see here, because we see in an modulus, as we know, modulus elastic modulus is an anisotropic property and the fourth rank tensor as well. So the modulus of the composite is not going to be the same as the same along A direction or the same along B direction. And if it is randomly oriented in a polycrystalline material, what we get is the E average from all dimensions. However, if we are able to orient it through some mechanical processing, let's say if we roll the sample, then predominantly all the grains tend to orient in a similar way. Or if we apply an external electric force, or if we apply an external magnetic force, any of these things to our uh, align our grains in a particular direction, then that is called as a texture material. So if we introduce texture to our material, it could be, rather than it being an average, it could be a cumulative. As we saw, E is cumulative, right? Uh, we can cumulatively add all these things, and it is definitely going to be higher than the average. So in this case, E UVW can be greater than E average. Okay, so that is the good thing about textured materials. Um, just a minute, there was one more point, and then yeah, finally we have seen the ways in which we can improve the overall elastic modulus. There are three ways of improving elastic modulus. One is composites, second is alloying, and third is texturing. Okay. Now we will come to the most important part of this week's classes. See, in a stress strain curve, we have the assumption that in a stress strain curve, we have the assumption that it is going to be linear as we apply load, and then when we release load, it is going to come back in the same way, right? But what if in certain cases there is a delay? Uh, Sorry, just give me a minute. In certain cases, what if there is a delay? There is a time delay during for my strain to exhibit itself. So I have applied an instantaneous load. I have applied an instantaneous load, and however, my material or my sample is unable to reach the maximum strain that it can achieve at this given load. I have given the maximum instantaneous load. Max strain is not achieved. What would happen in that case? So what has happened here is, okay, but right now what has happened is that at the same stress level, I have only been able to achieve this particular strain. Let's say this strain is epsilon I. This strain under adiabatic conditions is EA. Okay. Why did I mention the term adiabatic right now? What does adiabatic mean? It means no heat exchange to surroundings. Okay. So let's say if I have a steel plate, and if I'm pulling it or if I'm applying an instantaneous load, and there is some time delay for the strain to exhibit itself, there is no heat exchange between my sample and my surroundings in that small dimension because I'm keeping it at room temperature. Okay, or I'm keeping it in such a chamber, such a condition where I'm not allowing heat exchange to happen between my sample and my surroundings. So during this process, I achieve a strain of epsilon A. But however, if I leave my sample at sigma max, exposed to sigma max for some time, it eventually comes up to the point of epsilon I. Okay, this this time, let's say this time is there is some time delay. Later we'll understand that this is the concept of relaxation time, where it is same or delay time, and everything. The next step that I do is, once my sample reaches point A and the strain of epsilon I remove my load instantaneously. So this is the nature that I'm following. Okay, I remove my load instantaneously. Now what happens is that there is some residual strain that is left in the material even though I have removed all the external stresses. However, the nature of this behavior is such that when I leave it unexposed to any external stresses for a certain time, even with some remaining stress, retained stress, it is going to come back to the point of zero. Okay, so there's going to be this entire hysteresis loop that is going to be followed. Okay, and this hysteresis behavior is called as, okay, uh, this entire process is happening because of, it is happening at an atomistic scale, at a microstructural scale. Diffusion is a huge reason behind this, because um, diffusion is extremely paramount for this anelastic behavior or anelastic nature to present itself in materials. In order for this to happen, there should be some sort of diffusion, like say interstitial atoms should move, or substitutional atom should move, or grain boundary should move, or dislocations should move. Any of these can happen, any of these should happen, occur for the overall process to take place. So uh, from again, whenever there is diffusion, we know that it is going to be temperature dependent, and the time for a movement of an interstitial atom is going to be greater than the time required for the movement of a substitutional atom, because interstitial atom, let's say carbon, is generally smaller than an iron atom in the case of steel, in steels. So uh, smaller moves faster, larger moves slower. The time taken for this movement is again smaller, so which means that the time which in here is known as the relaxation time is dependent on temperature dependent. When diffusion the diffusion relation with temperature is governed by an equation by the nature of Arrhenius relation. We'll have a similar relation for our relaxation time as well, where tau equals tau naught into e power q by kbt, where tau is relaxation time, tau naught is standard time corresponding to natural frequency, q is activation energy, kb is Boltzmann constant, t is temperature. So if we want to increase the relaxation time, if we want to increase the relaxation time, T naught is going to be constant for a given material. Okay, we know that if we want to increase T, we have to increase the value of this exponent. For, for, for to increase the value of this exponent, we have to increase the value of this power of this power. So we can do that either by increasing Q or by decreasing T, because Kb is again constant. Okay, so tau will increase with increasing Q activation energy, or tau will increase by decreasing temperature. So these are two factors which are very important to understand the relaxation time. Uh, so in reality, so the square shape that we saw right now of this is not going to happen in reality. In reality, what occurs is that, right, where the let's say this OABC path is technically followed in this curve, in this is ideal, and this is the reality. Okay. Um, Also, in the case of Q, Q is high for substitutional and Q is low for interstitial. It makes sense because let's say I have a row of atoms. I'm replacing one atom. I'm substituting this atom, and I have an interstitial atom over here. For my interstitial atom to move from location A to location 1 to location 2. Similarly, for my interstitial atom, so substitutional atom to move from location 1, location A to location B. Do you think it is going to consume the same amount of energy for these two reactions? For this A to B is going to be much more, or rather, let's say, okay, for my A to move from A to B is going to be much more difficult um, rather than the small interstitial moving from 1 to 2, because let's just say the intermediate steps involved in 1 moving to 2 and A moving to B. For 1 moving to 2, we have this set of atoms. I'll just draw it much more simpler. I have this here. Next step is it comes somewhere in between so that the middle plane of atoms is displaced a little bit, and then finally we have our final set of atoms over here. Okay, so my interstitial atom has moved from point 1 to point 2 already right now, but in the case of my substitution atom, if it has to move from one point to other, it has to come closer to the first atom, and then sorry, it has to come closer to the first atom, and all these things should happen during a random oscillation between these two atoms correspondingly, right? After this step, it has to come above and beyond the existing atom in plane. This is my atom of interest. So this atom will come here, so it should displace basically, or rather it will displace this to an intermediate, this position over here, and then it will come here. This should move back again. So just see the amount of work involved in moving these two rather than the interstitial moving from point A to point B. The substitution atom would have to undergo a lot, would need a lot more energy to point come from point A to point B. So that's why the activation energy for this particular movement of substitution atom is going to be much harder, much more larger than the case of interstitial atoms. Um, I think I've covered most of it. Again, in elastic region, just like we are able to have a comparison between our stress and epsilon strain, we can also have a comparison between the temperature and the entropy of the system. Um, and because this effect is called as the thermoelastic effect. Why do we call it thermoelastic effect? Um, because with the change in entropy there will be a change in the temperature from the Gibbs equations, we know for sure, and there is a relation here where del tau by del epsilon, where if we want to correlate these two points at a constant entropy, there is a formula given where Vm is the molar volume, alpha is the coefficient of thermal expansion, into E is the Young's modulus, into temperature by Cv is the specific heat at a constant volume. And all these things, this constant H is basically is an isentropic process. It is possible to have an adiabatic system in isentropic process because there is no heat exchange involved. Once again, all these are a lot of assumptions uh, that are going to happen. Uh, and this is the correlation between thermodynamic properties and mechanical properties, and this is something very important as well. Yeah, so we did an example. I think I've completed everything. I'm not sure if I missed anything, but okay, yeah. So I think that's it. This would be the end of this class. We are already over the time limit by over 15-20 minutes, I guess. I'll try to pace my class better next week. Um, I'm I, I'll try if I have I'll think if I have missed to address any particular points from this week's class. If I have missed to address any particular points from this week's class, I'll definitely take it up in the subsequent classes, no doubt about it. And yeah, thank you so much everyone for attending. Um, if you have any doubts, please write it in the discussion forum in the Google groups, or you can write it in my comments here as well. All these videos will be uploaded on YouTube too, so you can feel free to watch these things for the second or third time if you have any doubts again. Okay. Okay. Thank you so much. I'll be ending the class here.